Now, this brings us to the topic of what happens with some of these bigger isotopes, like, for example, uranium. We were asking ourselves, uh, how do we use the energy that is stored in these unstable nuclei? We called it earlier the nuclear binding energy. Well, one process is what is called nuclear fission. Nuclear fission, if you bombard an atom of uranium 235 with a neutron, for example, at relatively slow speed, it can cause the nucleus to divide into smaller nuclei and in the process release one or more neutrons. This process generates tremendous amounts of energy. If you want, you can write out this equation, right? One neutron plus U-235, and then on the daughter side, you'd have strontium-90, xenon-143 plus 3 neutrons. Do the calculations that we've done before, where you essentially calculate what is the mass defect in these things, right? Remember that we would calculate what is the masses of all these things in the daughter nucleus and particles minus the masses of the uranium and the neutron. This would be the mass defect, and you multiply times the square of the speed of light, and you can calculate the amount of energy that can be released here. You could say this is a joules per unit, but let's talk about kilojoules per mole. We're talking about 2 times 10 to the 10th kilojoules per mole of uranium 235. Now, compare that amount of energy with the energy released by the combustion of 1 ton of coal, one of the right now less desirable forms of energy in our society because of its contribution to the carbon dioxide and in the atmosphere and other byproducts. This one generates essentially 50,000 kilojoules per ton. You're talking here 2 times 10 to the 10th kilojoules per mole of uranium-35. A mole of uranium-35 is what? About 235 grams or so. In other words, the amount of energy released by this process is tremendous. Not only that, notice on the right side of that diagram on the top, in the process, 3 neutrons are released in addition. So think about it. If you have a sample of uranium-235 atoms, now you have 3 more neutrons that could go on to collide and cause nuclear fission of other uranium-235 atoms. Okay, this is what is called a nuclear chain reaction. It's a self-sustaining sequence of nuclear fission reactions. So, for example, we started on the left with one single neutron colliding with a uranium-235 atom. That releases 3 neutrons. Let's say that 2 out of those 3 are able to collide with other uranium-235. And again, this could produce other types of daughter nucleates. Doesn't always have to be the same ones. The important thing is that each step now generates 3 neutrons, and so you've gone from 1 to 3 to 6, and therefore this could become a self-sustaining sequence. Now, this would only work if you have like the right amount of uranium in there. In other words, if you don't have enough uranium, then many of the neutrons are simply going to escape and collide against the reaction vessel and so forth. So we need a minimum amount of uranium to allow the reaction to continue. This is what we call the critical mass. This is the minimum mass of fissionable material required to generate a self-sustaining nuclear chain reaction. And of course, having at our disposal such a tremendous amount of energy, what did we use it for? For that. Just leave it to us humans to come up with destructive ways of applying something that is so potentially useful. I don't want to spend a lot of time on this, but essentially This is how an atomic bomb works. You essentially have on the two extremes of the bomb a certain amount of uranium-235, which is subcritical. In other words, you have less than the critical mass. So when the bomb essentially hits the ground and explodes, what you have is you have explosive material here at the tip, just regular TNT explosive. That explosion creates a pressure that pushes the subcritical amount of uranium-235 on that end to compress against the other one, and then you have other ingredients in there to generate neutrons, typically a mixture of beryllium and plutonium, and that is what starts the chain reaction. But let's talk about that. Let's talk about something else. There is a way, although in our society they've gotten a bad reputation, of using nuclear energy in a positive way. This is just once more a sketch of how a nuclear reactor works. So in this case, this is the same nuclear reaction, okay? It's still a nuclear fission. It's still a chain reaction. Notice, if you can see there on the bottom left, this is the reactor itself. Notice that it has the uranium fuel in the form of rods, and typically the uranium, there are different degrees, different grades of purity of uranium depending on the applications. So this is a certain grade of uranium, typically in the form of an oxide of uranium, and it's in these rods, and they're submerged in water. And then you have as a source of neutrons, you have these control rods that are drawn in green here, and these are made of cadmium or boron. This is basically the way that you control the number of neutrons. Because if you don't control the number of neutrons colliding with uranium fuel rods, you could have a massive reaction and the reactor core could melt. And of course, we all seen the movies about that, and we also know about accidents that have actually happened in nuclear reactors around the world. Now, the water here serves several purposes. Okay, number one, the water itself slows down the neutrons because you want to have actually slower speed neutrons because they're more effective in the chain reaction than faster moving neutrons. Secondly, you can see here on the top, let me use my marker here for a moment. You can see here where there is a water that's being sourced, and this water, because of the tremendous heat generated by the nuclear reaction, is getting vaporized. That steam is then used to run a steam turbine to generate electrical energy. Also, as the water circulates back into the tank, what it does is it also serves as a coolant. It helps to maintain the core at a decent temperature. Notice that there's a double shielding set of walls here. And the idea of the water, again, explains why usually you build these reactors near large bodies of water. As I said, this is just a sketch. I mean, the core, the interior of a reactor might look something like in this picture. And again, you can see that blue glow coming in there. That's what we call the Cherenkov radiation. This is essentially due to the ionization of air particles in the reactor that produce this blue glow. Now, there is another phenomenon that is called nuclear fusion. So remember, this is the energy that is produced by stars such as our sun. Now, in nuclear fusion, what happens is that small nuclei are combined to form larger ones. Now, if you remember back when we studied nuclear binding energies and their stabilities, remember that lighter elements are less stable than some of the heavier ones. So as you fuse two small nuclei to form a larger one, that should typically release a lot of energy. And this is how the sun is powered. So in the sun, what you have is several kinds of fusion reactions. mainly between hydrogen atoms to produce tritium or helium atoms. And then, of course, there's other reactions, usually producing helium. So essentially, these reactions occur at very, very high temperatures. Notice on the right side the amounts of energy that can be released by these reactions. We're talking about millions of kilojoules per mole, just like we studied previously with the nuclear fission reaction. Now, here's the thing, at least in theory, and at least when you look at these reactions in paper. Number one, hydrogen is a very abundant element in the universe. So we could say there's an abundant supply of quote unquote fuel. Secondly, notice that the products of these reactions are not themselves very high energy, unstable isotopes. For example, tritium, although it is radioactive, it is a low energy beta emitter. So it sounds like an ideal process for generating energy. However, there are a lot of technical obstacles to overcome. We're not there yet. These reactions have to occur at very high temperatures. Now, one of the things that happens is that, and again, this is the realm of physics. I'm not an expert, but at very high temperatures, you can have atoms losing electrons, molecules falling apart, and matter existing as kind of like a gas mixture of ions that is called a plasma. So a plasma might be a good place to work with these kinds of reactions, but it's hard to contain it. So one way of doing it is to contain it in magnetic fields. This is once more a sketch of something called a tokamak reactor, where you're containing plasma by surrounding it with magnets. Again, these things are still in the experimental stage. There's also another approach, which is to use lasers to transfer energies to a very small pellet to initiate the reaction. So once more, nuclear fusion is a little bit out of our hands at this point as a economically feasible way of generating energy, although in theory, we probably at some point will work it out. Of course, we have been able to generate energy from thermal or nuclear fusion. Because these reactions occur at high temperatures and they are, nuclear reactions, the word thermonuclear reaction comes to mind. And once we hear that thermonuclear, of course, what do we think of? Again, bombs. That's right. So a hydrogen bomb is a thermonuclear device. It's essentially a device where first you have an atomic bomb that explodes and generates a tremendous amount of heat that helps generate the fusion reaction. So a thermonuclear bomb, like a hydrogen bomb, generates a tremendous amount of heat and shock, but it doesn't generate the levels of radiation that the atomic bomb does. All right. Let's go back to more agreeable, more peaceful kind of applications of nuclear chemistry. One of them is, we've mentioned it before when we talked about the study of reaction mechanisms. So you can use radioisotopes to quote unquote label compounds and track specific atoms throughout a chemical reaction. This is the method that was used to essentially elucidate the mechanisms of the various reactions that form our metabolic pathways, right? So we can use them to study reaction mechanisms, we can use them to determine the structures of compounds, and so forth. Now, when we work with these types of studies, of course, we have to be concerned about health. So let's talk about some of the effects of radiation on life. Remember, we said radiation is high energy. It's enough energy to knock electrons off from molecules and break chemical bonds. This is what we call ionizing radiation. This kind of energy can damage biological molecules and thus cause malfunctions of cells. High levels of radiation, even over a short period of time, for example, from a nuclear blast, can kill large numbers of cells. But there are other effects that are caused by perhaps more gradual, less energy per se absorption of radiation. And it is, for example, a weakened immune system, lower abilities to absorb nutrients from food. Typically you can be more exposed to infections. And like I said, low doses of radiation over a fairly considerable period of time can also show an increased risk for cancer because of the damage to the DNA. All right, I'm going to go through this section here very quickly. I'm going to let you guys study most of this on your own. This is a cross section of our skin, and in terms of radiation and health, what's important is to understand what are the different degrees of penetration of these particles. You can see that gamma radiation, which is electromagnetic, not particulate, has the ability, the energy to penetrate all the way through the skin into our inner organs. Right? Beta particles can penetrate the skin, but they stay in those levels of the skin. They don't go all the way to the bone and the organs. And alpha particles do not penetrate the skin. However, there's a difference between radiation that is brought to us from the outside versus, for example, if you consume radioactive materials and the effect they cause inside. Once more, I'm going to let you guys read about that on your own. You're not going to be you're going to be required to know all this stuff for the exam, but I want to discuss it. For example, when we think about exposure to radiation, well, there's two factors here. One is the type of radiation, because remember, different types of radiation have different degrees of penetration, and also what part of the body is irradiated. So one of the things that scientists do here is they define what is called a radiation absorbed dose, or RAD. And essentially, 1 rad is 1 times 10 to the negative 5 joules per gram of material. Now, remember we said the type and amount of radiation, but also the part of the body. So we have what I call REMS, or Röntgen equivalent for man, which is essentially 1 rad times a factor called the relative biological effectiveness factor. Like we said, different types of radiation have different levels of penetration, and therefore they're going to have different levels of impact on our health conditions. So for a gamma ray, we assign an RBE of 1. We do the same thing for a beta particle. For alpha, we assign a value of 10. All right. So essentially, alpha particles are stopped by the outer layer of skin. We said beta particles can penetrate about 1 centimeter. But in the same way, if they are on the interior, alpha particles are going to be retained, and therefore they're going to basically bounce around, and as such are going to cause more damage than the gamma rays, which, curiously will basically go through our body to the outside. Okay, here are here's a table that lists some of the biological effects of different levels of radiation. Notice that this is pretty excessive. We're starting here at doses of 20 to 100 rams, which cause decreased white blood cell counts and possible increase in cancer risks and upwards of that. We are not normally exposed to these levels of radiation. People who work in nuclear industries and stuff like that, they wear a lot of protection, and as I mentioned earlier, they carry these different detection devices to make sure they're not getting exposed to more than what is allowed. But the reality is that we are exposed on a daily basis to different sources of radiation. There's very interesting things as I've been reading. For example, per year you are exposed to radon gas, which is natural, to about 200 milligrams per year of that type of radiation. Notice that an X-ray, a mammogram, a barium study, all these things, they all expose you. And of course, that's why they will ask in the doctors if, for example, in the case of a woman, if she is pregnant, or for example, in the case of anybody, if they're taking any kinds of medications that might decrease their immune capacity. It's interesting, I was looking at this over here, it says building materials. Well, it turns out that in most houses in the foundation or wherever, there are sources of radiation that we might be exposed to on a yearly basis. None of these really are of great concern. For example, you don't take x-rays like every day, right? Women do that mammogram maybe once a year, something like that. So, you also have to take that into account. The other application that is interesting in terms of radioisotopes is that we can take advantage of how easily they can be detected, and also how there are certain substances that have specific affinities for or compositions that include these isotopes, and it allows us to use them as what we call radio tracers. For example, here's iodine 131. It turns out that the thyroid gland uses a lot of iodine in its metabolism. And so you can use different kinds of iodine isotope compounds to detect the images of the thyroid. We convert the energy of these into an image, and you can see here an example of thyroid glands that are normal. And here's another one where you can see an abnormality in there in the amount of iodine, which might include, I'm not a doctor, I think might be called hyperthyroidism, maybe, something like that. There are many studies that take advantage of these. You may have heard of PET scans. This is something that is used to detect, for example, a patient with cancer, to detect if any of the cancer cells have metastasized, in other words, have they moved into other parts of the organism. So PET stands for positron emission tomography. So we use them to detect tumors in different parts. For example, fluorine 18 can be attached to glucose. Tumors and the brain use a lot of energy. As a matter of fact, the energy of the brain comes from metabolism of glucose. The brain does not typically metabolize other carbon sources to obtain energy, only glucose. And so when F18 decays, it emits positrons. And so PET scans essentially detect this. You can see, for example, here on the right, a PET scan before and after a cancer therapy. You can see here on the right, and you can see the decrease in the tumors that are visible through this technology. You can also see here on the left scans of a normal brain, brain with mild cognitive impairment, and then a brain representing a patient with fully developed Alzheimer's. So these are very interesting uses. Like I said, humans have the choice. They have the power to decide how are we going to use this type of chemistry. There are many, many ways of using it for the betterment of our lives, for the improvement of our diagnostic techniques, and definitely, hopefully in the future, to generate safe energy along with other methods that we are in the process of developing.